everyone. In this lesson, we're going to be looking at how to do a second degree algebraic solution for modeling a curve. Now here we go. I've got the quadratic formula, second degree. There's three different ways we can express a quadratic equation. We have standard form, we have turning point form, we're probably most familiar with those two. And lastly, we could have in factorized form. So if imagine we took a common factor of a from the standard form, we'd be left with a monic quadratic, and then that monic quadratic would have two roots, perhaps two different roots, perhaps the same, and we could have x take alpha, x take beta, where alpha and beta are the roots of the equation. So let's see how this might happen. So I'm going to be demonstrating this with the use of a piece of software called GeoGebra, which is lovely software, completely free. This is the online version. I'll be starting off with the tools, and I'll be selecting an image. I'll just have a quick browse. That's the one that I want. Here it is. Now once the image is in place, I can use these points at the bottom to resize or change the orientation of the image. I might make it a bit bigger. And the other thing that I might like to do is a right click on the image itself, go to the settings on the color, and just reduce the opacity a bit so that I can start to see the grid lines showing through behind the image. Now I'm interested in modeling a second degree, so I'm looking for an even degree polynomial, one where the outside arms of the curve both face the same direction. I'm thinking the front of this leg here around the knee and then up towards the ankle might be a good candidate for this task. So I do want to make my image quite a bit larger so I can see that clearly, and I'm going to be a bit careful about how I do this. I definitely want to have the horizontal axis cutting through this curve. I want to have this, whatever quadratic formula that I end up making, I want to have it so that there are two roots to this equation. So I can zoom up even further. Now that looks pretty good. I want to start the curve there, I want to go around there, and I want to stop it about there. So I'm going to start placing some points on the curve. Now you select that tool. I'll place a point here at the first root, and then I'll place another point over here at the second root. I'll check the values of those. So don't worry about point A and point B. They were the points at the bottom of the picture. It's point C and point D I'm interested in. Now, it seems like point C and point D are close to zeros. I've got the settings here. So if I go to the settings and then again the cog, I've got three significant figures. It might be better off if I just display, say, 2 decimal places. Now, my second point, point D, is not quite on the axis, so I'll have to zoom right in here. Yes, it's a little bit low, wasn't it? So I might just shift it to there. And it's a bit of a guess between where the red stops and where the white starts. So once I've zoomed out, that looks all right. So there's my 2 points, 50 and 10.350. So I'm just going to pop back to my notes for a minute, and I'm going to use this form of the quadratic equation because the roots of the equation are this number and this number. Now, in our case, we could see the roots are 5 and 10.35. So let's start writing that down. So we had that the first root of the equation was 50 and the next one was 10.35. So let's substitute. We'd have, don't know the dilation factor A yet, but we'd have x take 5 and we'd have x take 10.35. So we're off to a good start. We still need to find the value of A. So we would have to go back to our diagram and we'll need a third point. So on the tool menu, I'll select points and I'm going to pick a point. So I wanted to go from all the way there, down around the knee, up to there. I'm going to pick a point somewhere in between them, and I don't really want it to be the turning point. It's hard to guess where the turning point exactly is. So I might try to pick that point there. And that looked like very close to 8, isn't it? Let's just zoom on in and see if I can fudge that slightly to make my life easier. There it is, 8 and -1, and it still looks like it's on the boundary of those two. I might have fudged that slightly, but you won't tell anybody, I hope. So there's our third point, which is at 8, -1. So I am going to now substitute the value 8, -1 into this equation. So the y value would be -1. We don't know a. X value is 8 subtract 5, and then 8 subtract 10.35. 8 subtract 5, of course, is 3. 8 subtract this is -2.35. So I end up with -1 equals, now that times that, well, 3 5s are 15, carry a 1, 3 3s are 9, and 1 is 10, carry the digit, 3 2s are 6, and 1 is 7. I think that is -7.05 times a, so 1 over 7.05 should equal a, and that will be a job for my calculator. So I want to know 1 divided by 7.05, 0.1418. Looks like it's pretty close. 0.1418 is the value of A. So my formula then, I'm going to suggest that my equation for a quadratic that would fit those points would look like this. And I think the last one was 10.35, wasn't it? Yes, 10.35. Oh, it helps if you write 10 first. Here I go, 10.35. So we've done algebraic work. Yes, we used a little bit of software to select the data points, but I think if I was to type that equation into my GeoGebra, we might get something interesting. So let's see what happens here. I'm going to go f of x equals 0.1418, which is rounded, but it's okay. X take 5, then x take 10.35, and away I go. Now that's not too bad. I mean, I'm happy with that. I hope that is okay. Just going to move the whole picture up a bit there and zoom up a bit. So I was trying to get a second degree polynomial that would match the 3 data points I selected. Well, I've succeeded there. Those 3 data points, of course, if there's 3 data points, you have to be able to get a perfect fit to a second degree polynomial. How did I go with matching the shape of the curve? Well, there's a bit of a gap here. It's pretty good where the 3 points are, although maybe the red quadratic's a little bit too high here. And then I sort of missed I was trying to stop at the ankle. When it curves back the other way, I wasn't interested. So I'm trying to go about there. So I really want to limit the domain of this graph. So the starting value should be about 3, and the finishing value there should be, well, that's 11, maybe 11.5. Let's see if we can do that. Now, there is a way in GeoGebra. We have to use the command, I'll give it a different name, g of x, and we have to use the command function. Now, I will tell it to use function f. Start from the x value of 3, and I think I said I wanted to go to about 11.5. So I'll draw that in. Now, if I turn the first one off so we don't see it anymore, now this g of x, it starts there, does what it has to do, and stops at 11.5. It's close. It's a preliminary model. It's not my final answer, but it's a good start. All right, that's it for now. Hope that helps. See you next time.